To introduce this next talk, I will first ask you another question. Has anyone here ever had the chance to send something into space? One person, two persons, three. Well, more than I expected, less than I hoped for. This next talk might be giving you a small introduction to how to do that. So our next speaker, let's just call him Inko, has studied first in Brunswick and built hydrographics with the ERIC, which I am proudly representing here, not an advertisement. And then moved over to Kiruna, where he studied space science and then designed a CubeSat. For the next hour, he will introduce you to this topic, and I hope he will answer this one important question. How hard can it be? Audience, give a warm applause to Inko with "So you want to build a satellite?"
Yeah, thanks for the introduction. As has been said, I've studied in Kiruna, and up there we have reindeers, iron ore mining, and space research. And I just want to give you a brief glimpse of the complexities of designing a spacecraft, especially a CubeSat. So what is a CubeSat? A CubeSat is a pico or nanosatellite following the CubeSat standard. A pico nanosatellite is a satellite which falls in the arbitrary weight class of 1 to 10 kilograms. And the special thing about CubeSats is inside the pico nanosatellite class that they are launched not only as a secondary payload, but as a containerized payload. I will later tell you what this means. And the interesting thing about CubeSats are that they provide a relatively low entry hurdle into satellite technology. So a short history about CubeSats. There were small amateur satellites before, especially amateur radio satellites, which acted as relay stations for amateur radio users, but most of them didn't follow any standards, so there was a lot of reinventing the wheel. With progressing miniaturization of electronic components, it was possible to shrink these small satellites, which formerly had about a cubic meter maybe in size, down to just the CubeSat's form factor. And therefore, CubeSats were invented mostly as a way for students to learn how to build a full-fledged satellite without having the long delay with previous small satellite projects. But since then, CubeSats have not only been used in educational context, but also in scientific research, in technology demonstrations, and even as commercial applications. So what is in the CubeSat design specifications? Most importantly, it defines the CubeSat's shape and mass, but also it defines what makes the CubeSat so easily transportable as a secondary payload. So for example, it ensures that the launch vehicle is safe from the CubeSat, but also that the launch provider doesn't have to worry about any liabilities for not adhering to regulations. So mostly with regards to radio communication and orbital debris. But in general, these standards inside the CubeSat design specification, this is the official document you can download, is just the minimum common denominator between the different launch providers of CubeSats. So if you adhere to this standard, you will definitely be fine, but often you can hand in waiver forms which give you small exceptions, or even the CubeSat provider offer more volume in certain directions or something like that. So the CubeSat envelope, basically almost a 10 by 10 by 10 centimeter block. I heard chosen to teach the metric system to American students. It's not really 10 centimeters in height because we have small standoffs here, but close enough. And on the edges, you have these guide rails, which have a defined minimum hardness, because those are important to hold the CubeSats in place and later put them into space. So and from these space units, you have different defined form factors, usually whole multiples of the base 1 unit, so 1, 2, 3, 4, and so on. But sometimes you also see half unit CubeSat or 1.5 units. So another standard you might encounter is the CubeSat Kit bus PCB, which follows the PC104 standard for the shape of the PCB and the mounting holes, but has a special 4-row connector. And on this 4-row connectors, you have common voltages, battery voltages, digital buses, general purpose IOs, And a lot of commercial CubeSat components and subsystems you can buy follow to this form. Of course, this is a pretty big PCB, and some manufacturers have gone on to define proprietary formats for fitting more functions in this same PCB form factor with subboards and so on. Something which you might find unusual is that the mounting holes are not really symmetric, so you have to pay attention how to mount this thing inside your structure. And these PCBs are then stacked, and the connector here is just for the electrical connection. The real mechanical connection, which holds the PCB inside the CubeSat structure, is done via threaded rods inserted here in the edges, and then the PCBs are held together with spacers. So how is a CubeSat launched? CubeSats are integrated in so-called pod dispensers. So here you can see 6 pod dispensers in a bigger box, and this dispensers are then mounted on the upper stage of the rocket. So for example, on the payload adapter, somewhere in between, or even below near the engine. And after the main payload is gone and it had a good head start, so you can't hit it anymore, these pods are opened and the CubeSats are released. Here you can see such a pod. So the most important the work this pod does is it contains the CubeSat during launch. So it holds it in place, and even if something breaks inside the CubeSat, it will not hurt the main satellite, because this is all the rocket operator cares for. So you integrate it into these pods, and this is basically the last time you see your satellite. It has some access hatches to remove arm and safety plugs after integration, but then it's integrated, it's shipped to launch site, and you don't see it anymore. Inside this CubeSat, in this case a 3-unit CubeSat, is held by rails and sitting on top of a spring-loaded pusher plate. And then when time comes and you're in space, the box opens and the pusher plate just pushes out the satellite into space. So some words about payload safety. The CubeSat design specifications have a couple of them. So for example, the payload has to be dead during launch, so there is no power going anywhere inside your satellite. The batteries and solar panels are physically, via launch switches, separated from the electronics. This means that you get no communication after integration. You also can't emit any RF frequencies or magnetic fields by accident, and therefore ensure that you're a good co-passenger. Also, of course, because the pod has to contain your satellite, you are also not allowed to have very high density of energy inside your satellite, because that has the potential of getting out of the pod. Let's put it this way. So this is especially important if you want to have some pressurized containers on board, or if you would have, if you wanted to have a kind of propulsion, for example, a chemical propulsion. This is usually not possible because of this energy limit. There are further limits, for example, on hazardous substances. So the workers on the ground are safe from your satellite, or also on volatile materials which evaporate from your satellite and might recondense on other people's satellite, on their optics or something like that. So this is not allowed. So I just want to go over the most important subsystems of CubeSat, which you can see here. They are mostly similar to big satellites. It's just the difference is that they are miniaturized, and you have a much tighter integration between the different components. So you will see that there are a lot of interdependencies between these subsystems. So starting with mechanisms and structure. So a mechanism and structure is everything that holds things in place or makes things move. And you have to see that mechanisms are common points of failure in space projects. So it's important that if you don't want to be one of the 50% of first-time satellites, first-time CubeSats, which fail without doing anything significant in orbit, you have to verify them. And the common mechanisms include, for example, antenna deployment. If you have external deployable solar panels, they can be deployed. And this is usually just done by spring-loading them and holding them back by a burn wire, which you burn in orbit and then it releases. So verification, what are common verification methods? For example, for launch vibration, the vibrations during launch are much more severe for your satellite than just the static G-loads. So how do you find out what kind of vibrations you expect? You could read the manual. Nearly any major commercial satellite launcher has a publicly available user manual, so Ariane 5, Soyuz, and so on. So you can just find it on the internet. The problem is they give you a vibration profile which is meant for the main main payload, and you're mounted inside the pod on somewhere else on the upper stage. So you would need to know the behavior of the pod and the mounting to really know what your satellite feels. So it's better to just look at your CubeSat launch provider. They also have documents, and they specify an acceptance level of vibrations you have to withstand before during launch. So that's usually what you test for. And for mechanisms, of course, it's usually easy to get it working on Earth under ambient temperature and so on. And so it's very important, if you have a crucial mechanism, that you test it under the conditions that you might actually encounter in space. So for example, after it has been shaken from the launch, or at the temperature profiles you encounter in space, so it might have different expansions and might stuck, or vacuum might be a factor, and also low battery levels. Because if you have burn wires and you want to deploy your solar panels and you don't have enough battery, how do you get more battery power, because you can't deploy your solar panels? So please test them also under these circumstances. So next, a few words about thermal. So there was often the question, is space hot or cold? It totally depends, because in space, due to the lack of atmosphere, the heat can only be transported over conduction inside the satellite, radiation inside the satellite, and to the outside only radiation. And due to the small thermal mass of CubeSats, you can get very high temperature variations even over one orbit, so from in the eclipse period inside the shadow of the Earth and then in the sun. So for example, the FunCube satellite would publish its data online, has surface temperatures from minus 20 degrees to 40 degrees, just maybe over one orbit. So what you get is a radiation balance between solar radiation, also some reflected solar radiation from Earth, also emission of thermal radiation from Earth, and then of course your satellites heats up, also emits thermal radiation, and then you get a kind of balance, or let's say a budget. So what can you do? For externally, usually you can just on CubeSat level change the absorptivity and emissivity values of the surface. So let's say the color of the surface for IR radiation and so on. The problem is that a large contribution of the surface will be covered in solar panels, because you really need this power. So you can't really just make it reflective. That would be not a good idea. What you can do, for example, if you have a problem with uneven heating, if you have one side of the satellite which might always face the sun and overheat, while the other one is relatively cool, you can go in something called a barbecue mode, which basically means you rotate your satellites and make it crispy from all sides. Yeah, but internally, if you have some very sensitive, heat-sensitive components, you might want to insulate them to keep them away from these huge temperature swings you see on the outside of the satellite. So for example, you can start by insulating the side panels, so these most important swings are kept away from your inside. But then you also have to see that the heat you generate with electronics inside or with heaters inside has to go somewhere. So you need some kind of conduction path to the outside. But this is a very complex trade-off. So how can you verify it? First thing you could do would be just think about if the satellite would just be masked with a surface in orbit under certain illumination conditions, would it heat up to a certain temperature, or would it cool down to a certain temperature? So what is the radiation really balanced temperature of the satellite? It just gives you a first idea of what problems you're facing. But in the end, you usually do a finite element analysis and try to just calculate what is the temperature difference, temperature distribution inside your satellite, especially because with this Earth shadowing time and then time in sunlight, you really have a transient behavior you want to know about. And then to finally verify it, you usually do a thermal vacuum test also to know if the models you did here have anything to do with reality. That isn't always the case. So thermal vacuum, because of course, if you would have convection, this changes the physics a lot, because this is much more prominent. So you want to do it in a vacuum environment. And of course, you might think, okay, this is relatively late in the development schedule because you already need your components. And maybe if then there is a major problem, this gives you a lot of problems because everything else is already developed. So maybe in the early stages of your development, you want to test just a structural model with resistor heaters as dummy loads, basically, for heat. So to the attitude determination control subsystem. So the attitude is the orientation of the CubeSat in space. You can define different frames you want to know your orientation in. Inertial frames, so non-rotating, basically with regards to the stars. Earth-centered frame is interesting if you want to do Earth observations. Sun-centered frame is interesting if you want to know something about the thermal conditions or your power generation. And for control, what do we have to work against? So we have to work against radiation pressure from the sun, magnetic torque with regards to magnetic cleanliness. So magnetic cleanliness basically means if you have built your satellite and launched it into orbit, you might not have built a satellite into it. You might, but that comes later. But if you don't want to have a magnet in your satellite, you still have some kind of magnetic field. So for example, because you have magnetized materials inside, or just because of the currents flowing inside your satellite. And this creates a torque with the Earth magnetic field and gives you a disturbance. But also if you have maybe a little bit larger CubeSat, you might encounter uneven drag. For example, if you have a deployable solar panel or something like that. So even the not very dense atmosphere might give you some kind of disturbance torque. And if you would have a really big satellite or maybe have a tether or something, just the changing gravity with height induces a torque trying to reorient the satellite. So how do we determine our attitude in space? The simplest way would be just use the illumination. So this just measures the illumination of the sun, the solar flux on your sensor, and then says, okay, I have a sensor on each side of my CubeSat, and then I try to determine from where the sun comes. Of course, you always have a degree of freedom rotating around the direction where the sun comes from, because this doesn't change the reading. But this gives you a reading in the sun-centered frame. Then you have the magnetic field. So as everyone knows, who has a smartphone, you can use the compass to determine the way you're heading. You can use a more sophisticated sun sensor. This is different from the illumination sun sensor in that you usually have some kind of baffle system which projects like a slit of light on the sensor, and then you can determine directly an angle where this light came from. So this is more accurate. You can use Earth horizon sensors, which basically try to detect the Earth or just the line where Earth meets space, and then you get a reference in the Earth-centered frame. And the highest class usually are star cameras. These are literally cameras looking at the stars, and then from the picture they see, they are looking with an algorithm in a star catalog and trying to determine which stars they have seen just by the brightness, the relative positions, and so on. And from that, you really get a good knowledge about your attitude. So why would we control attitude? So after deployment, due to the deployment mechanism with the pusher plate, you usually have some tumbling. It's not perfect. So if you think you can just be still and then do nothing, of course you have disturbance torques, but you also get tumbling from the start. Then of course you might have a payload which requires pointing, so your camera wants to look at Earth or things like that. Then you have antennas. If you have directional antennas, they want to be pointed to the ground station. And also if you have antennas which are nearly omnidirectional but have some zeros, some places where you don't really radiate anything to, then if you just tumble, you get just fading signal. So this signal goes down and you might not be able to send a complete packet. And of course, if it is too excessive, the antennas might actually bend and then they are behaving completely different because RF is black magic. So another important thing is power collection. So especially if you have a deployable solar panel, you really want to use it, then you of course should try to orient yourself towards the sun. And then you also might want to have attitude control. And what problems do we encounter? I mean, if you think about normal motion, if I push something in a direction, Newton says it should start to move in this direction and continue to move in this direction. This is nice. In rotation, if I just would give a torque around an axis, it would probably just start to tumble. The problem is that if you look into the physics, the motion around just arbitrary axes are usually coupled. So yeah, this is basically matrices which come into play here. And there are only 3 defined distinguishable axes in each solid body where you don't have any coupling, the so-called principal axis. But only even 2 of them, the motion is stable. So if you just have a small disturbance, one of the 3 axes will again start to make a tumble. So if you want to have a satellite which moves around a certain axis, maybe because you want to have a measurement or something like that, then you should think about distributing the mass inside your satellite so that it's easy for the control algorithm to control it. So maybe choose a principal axis for that, which is stable. A couple of methods how to stabilize a satellite, especially a CubeSat. The easiest way would be passive magnetic stabilization. You, by choice, put a magnet in your satellite, which is fixed to the frame. And it, of course, tries to orient itself like a compass needle to the Earth magnetic field. The problem is, of course, if it starts to orient itself, it gains kinetic energy and basically then goes into a pendulum oscillation. So you also want to have something which dissipates this movement away. So you also have hysteresis rods here out of hard ferromagnetic material in each direction. And inside these, the movement is then dissipated. Of course, there are limits because, I mean, it's easy, so it has to be somehow flawed. So you have interference with your attitude determination. I mean, if you build a huge magnet inside your compass, then it will not work anymore. It's not easily changed for a fixed position over the Earth because, I mean, if you really build this hard into your satellite, then maybe you can use it to point your satellite to your ground station when it's directly above. But in any other position above Earth, you don't really have any wiggle room to readjust your position. The accuracy is not good, and of course, you still have a degree of freedom when it just rotates around the magnetic field line, because then there is no torque applied. And you might have deployment problems, because if, let's say we have 2 of these in one deployment pod, they are pushed out, and then they just attract each other. That's not good. So the next step up, let's say, is active magnetic control. We have electromagnets inside the satellite. So for example, air coils integrated into the CubeSat panels here, or maybe also magnetorquer rods, which are just slender electromagnets inside the satellite structure. And yeah, just by controlling the current going through it, we produce our own variable magnetic field. So we have a lot more degrees of freedom to control it and move the satellite around. So for example, in combination with the magnetic attitude determination, we can use something called a B-dot algorithm to just detumble the satellite. So then afterwards, it's just spinning around one axis. That's nice, but of course, this, as opposed to the other one, uses power. Power is scarce, and again, you have 1 degree of freedom. So if you're, let's say, spinning around the magnetic field line and you want to stop that, there's not much you can do. So even more accurate are reaction wheels. They're basically flywheels with an electric motor, and as you know, actuator is reactor. So if we put a torque on the flywheel, the motor itself and the whole satellite it's mounted to will get a torque in the other direction. So with this, you can get very high pointing accuracy. The problem is, for example, if you have a disturbance torque, which always has a bias, so always tends to push you, let's say, clockwise, then you always have to apply a counter torque in the same direction. So you add spin to the wheel and spin to the wheels until maybe the bearings fail. Of course, you don't want that, so you need to have the way to have another type of attitude control to desaturate your wheels. And of course, this needs also power and needs continuous power, because if you would just stop power to the flywheels, then they would slow down due to friction, and this would give the torque you put into them back into your satellite. So the whole thing starts to spin and tumble again, and you usually don't want that. So again, this needs more power. A few words about communication. So telemetry and telecommand, if you can't get data to your satellite, if your satellite doesn't respond, then the satellite is bust. So you really want to have this thing nailed down. First measure, usually after you're deploying your satellite, or if there was any fault and the satellite goes into a safe state, it starts to transmit a beacon, which is just a short package burst, which includes the most important telemetry values of the satellite. This A helps you to locate your satellites. So for example, after launch, you have just a flock of satellites which were released. You don't know which one of these is yours, so you just try to ping each one, and whichever sends your beacon might be the right one. So yeah, if in case of a failure, you just get the most important values. You need to debug the problem, or at least find out what's going on. So different types of antennas. The easiest type of antenna are just these kind of extending rulers. You bend over the edge and hold down. So if you burn this wire, it flips up, and you have a working antenna if you did everything right. You have to distinguish between directive and omnidirectional antennas. So these types of antennas are usually near omnidirectional. So they have monopole-dipole return side configurations, and they are very good for, let's say, lower frequencies. If you want to have a directive antenna, you usually go to higher frequencies, because there it's feasible to construct such an antenna. Because the same structure used, for example, here for this antenna would be much, much larger if you go to these frequencies here. And yeah, basically here you have a patch antenna, which really just is a patch. Helical antenna, of course, here you would have another point of failure because you have to deploy this in orbit. Yeah, but these are the most common forms of antennas we see on CubeSats. So just a few words about frequencies. Common CubeSat frequencies, if you come from the amateur radio edge of the spectrum, are 70 centimeters and 2 meter frequencies, so about 430, 144 megahertz. Very common, long time use for amateur radio purpose. And the nice thing is, because the frequencies are relatively low, you have pretty efficient components. Problem is, because the frequencies are so low, the available bandwidth, or the bandwidth you are allowed to use, is relatively small, so you get only about 9.6 kilobits per second, while the satellite is in reach of your ground station. This is only just a fraction of its orbit, so you need a lot of orbits to get, let's say, a picture down. And of course, the high gain antennas for these wavelengths will get pretty big, and you can't put this on your CubeSat probably. So you might want to go to higher frequencies, especially popular with commercial CubeSats, which get different kind of licenses, so usually not operated under amateur radio regulations, and those get signal rates up into the megabits per second range. So that's much nicer because they have more bandwidth available, and if you don't need your higher data rate, you want to use less power, then you can also use the higher bandwidth to increase your link budget, so the transmission is more reliable. So just a few words about protocol, and really just a few. Common protocols you might want to look into if you are interested in things like that would be AX25, which is the amateur radio, packet radio protocol, which is has been used for lots of CubeSats, especially in the older days. If you want to take a look at a satellite communication protocol, which is a little bit more advanced, which is also used for big missions and big satellites, you can take a look at the available documentation on CCSDS, which is used for ESA missions. And yeah, please note that especially if you need a good connection, for example, if the satellite just started tumbling, you want to recover it, then it's important that you can that your protocol is able to work with a weak signaling. I heard of people trying to log on with SSH on their satellite. Not a good idea. It needs handshaking. So yeah. More on regulation. So of course, if you want to use amateur radio frequencies, you are, as an amateur radio user, usually allowed to use them, but you should go through a frequency coordination step, which just makes sure that there's no other satellite in similar orbit sending on the same frequency. And then you get a lot of restrictions based, which vary between the jurisdictions based on, for example, are you allowed to use amateur radio if you get a government grant, or is your ground station operator allowed to be paid for operating ground stations, things like that. But in general, there's at least an exception for commands being sent to the satellite because they are allowed to be encrypted. Everything else under amateur radio regulations has to be clear text, so it has to be readable. It might be compressed, that's okay as long as it's documented, but commands to satellite is the only thing that is allowed to be encrypted in amateur radio. And what's also important is that you have a fast and permanent transmission kill switch. So if your satellite goes haywire and just sends carrier on your frequency, you have to be able to shut it down. And fast could even mean that you need multiple ground stations in middle latitude. So we get it on the, let's say, in half a day or so. And permanent really means permanent. So there has been a satellite which has been shut down, but then there was a reset and it started to transmit again. That is not good. So please really make it permanent. So if you're not operating under amateur radio license, you have to talk to your national frequency coordination agency. And then you can get something like experimental permits or things like that, which allow you to use similar frequencies, maybe even in the same range, and yeah, get a little bit more freedom in what kind of applications you use here. So, but please note that frequency coordination and allocation takes a lot of time. So it would be bad if your satellite is built, ready to launch, but you don't have your allocation yet. So please look into it early in the project. So electrical power systems. It's all about power. So usually for power collection, triple junction solar cells are used. They're pretty efficient. We have a maximum peak efficiency of usually 27 to 30% if they are lit directly. And afterwards, you usually have a maximum optimum power point tracker, which adjusts the load the solar cell needs so that the power which is sucked out of it is optimized. Because otherwise, you might, especially with this low voltages you have on just a few cells on the CubeSat side, you don't really get the maximum power. But of course, you lose some power also due to these things. So as every real circuit, it's not really 100% efficient. But let's say near the Earth, you get about 2.3 watts per CubeSat panel when they are illuminated perpendicular. So if you have a satellite which is rotating, then you would get a slightly varying power intake. And on power collection, please remember to include a charging connector for testing and also for storage, because it is not very nice if you would have to put your satellite under a lamp every time you want to charge it during testing. So how could we increase this power collection? Obviously, we could try to increase our solar cell area. So here are a few common things you commonly see. So for example, just wings falling out or flaps going up. Of course, if you look at this configuration, when it's stored, it looks like this. This might not be a nice thing if you have to recover your satellite. Something went wrong during early phase because then the battery drains. So you might also want to include a few solar cells here on the outside. But then, after they're deployed, they are shadowed. And shadow solar cells tend to become loads if you don't include extra protection circuits. So please, look into it so this doesn't eat up all your power and gets hot. So if you have collected your battery, your power, you want to store it usually. So often lithium batteries are used, which are for just the satellite bus, usually the most temperature-sensitive components. So you want to keep these happy. Usually they are coming pre-integrated with a heater, so at least you don't freeze them. But what kind of capacity you need? So you have to supply your satellite with power throughout the eclipse period, so the period in the Earth's shadow. But also if you have short bursts of activity, so for example transmission, if you have a payload you have to operate, then you need just short bursts of power. And this is also cared for by the buffer of the battery here. The problem is if you just look at the advertisement and see 10 watt-hour batteries and you calculate, yeah, it should be enough, you usually are only allowed to discharge 20% of that. The reason is that if you think about your phone, I mean, it maybe the battery lasts a year without that much drop in capacity, but in a satellite you have a discharge cycle maybe every 90 minutes. So you really want to limit your depth of discharge so you get maybe 2 years out of the battery. So what about verification? Yeah, it's important that you really test the whole power chain as one. So maybe get some kind of lamp which simulate the solar spectrum and then see if really your battery gets charged, if your consumers can get the charge from the battery and so on. And also make sure that the efficiency values are according to your calculations, because often in the data sheets, even if you are buying a satellite electrical power supply, you only get one efficiency value, which is really not enough. So please make sure that the efficiencies that occur under your operational profile are such that you don't run out of power. Onboard computer. So really, if you look at flown onboard computer systems, you see everything from really small microcontrollers to embedded CPUs you can find in phones. Sometimes onboard computers are phones, but this is not so often. But you can also see some FPGAs which have been flown in CubeSats. And of course, in space, you have to deal with a different radiation environment than you find on Earth. And there you have two types of effects. One, single event effects, for example, latch up, more on this shortly, and bit flips and memory corruption. This later just messes with your program. This can damage your software, damage your hardware if you don't account for it. And then you get total dose effect, which don't happen instantly, but accumulate over the life of your satellite. And usually this leads, for example, to an increase in power consumption of your electronics. So if you size your power system, take this into account that you have some headspace for later in your satellite's life. So what are latch ups? Latch ups typically occur if a heavy ion or proton hits a CMOS device and then activates a parasitic transistor. If you look at the typical CMOS device structure here, there are these two transistor structures here, which are not really intended to be there, but just because of the structure, they can be there. And now we have a particle going in here, creating charges, and those two are activated. They're basically short-circuiting your supply. And this is, of course, not good because it heats and damages the device. So if you are seeing a sharp increase in power consumption, then it's a good idea to just reset the circuit, because this will not turn off until the power is taken off and put back again. This is for just commercial off-the-shelf circuits. If you have a, let's say, better hardened integrated circuit, then you sometimes get insulated substrates. So maybe it's on a sapphire or something like that. And there, this kind of problem is prevented. But this is one of the main reasons you often get resets on your satellite, just because the power supply detected the latch up and resetted the whole system. So this latch up protection here is often integrated into the electrical power supply if you're looking at commercially available CubeSat power supplies. A few other effects on electronics which you might not have heard of. Soldering whiskers are small, really small tendrils which are forming from soldering points, but they are big enough that they might bridge to another voltage potential and then create a short circuit. And this is especially problematic if you use lead-free solder. So that's the reason why space applications are usually exempt from using lead-free soldering. Another thing, especially for launch vibrations, it's always good to have strain relief. So if you want to solder a cable to your PCB, think about just putting it once through and then up, so you can inspect it from the top and have some kind of strain relief here, so that when the vibrations kick in, you are not damaging your soldering point. And always, of course, remember you don't have any convection. So if you find formulas describing how to size your lanes on your PCB to withstand a certain amount of current, think about if it's also the same under vacuum conditions without these cooling effects, because now you have to dissipate all your heat through your PCB. Few things about programming. Unscheduled resets are to be expected. So if your program has any problems with that, then you should rewrite it. For example, if you have some state which must not be lost, you have to save it in non-volatile memory, obviously. And which also sometimes creates problems is timing synchronization. So after a reset, if your satellite has no idea which time it is, it might not be able to perform important work, send when it's over a ground station, things like that. So for example, there was one satellite which couldn't complete a mission because its timer reset at one point, and the sequence just didn't get through. And then also, as I talked about earlier, there are bit flips, so just your program code not get corrupted. So it's a good idea if you have a bootloader. If it's not integrated into the silicon of your processor, then just have a small, very compact bootloader, which is unlikely to get hurt, and which maybe checks itself and also the other software program prior to execution. And then if you have the space, maybe have several copies, so you can at least reconstruct your program code afterwards. And if you want to update your software in space, of course, there's always a risk associated with that. If you have really a long-term mission, you might want to do it. So then maybe space it a little bit apart. If you have different software, different code blocks which fall out of your compiler prior to linking, maybe have a linker file which spaces them apart in your memory, because then you can overwrite parts of your memory without having to shift back all the things that come after it. So this would make it easier to update the software in space, because you just have to make delta updates instead of reprogramming the whole non-volatile memory. Just some miscellaneous things about orbits. So available orbits are mostly dictated by what kinds of launches are available, because you're only secondary satellites. There are some startups which try to build rockets just for CubeSat launches, but they haven't materialized yet. So just a few common orbits. Low Earth orbit from with ISS deployment, they really don't have such a long lifetime, maybe a month depending on your size, but they are relatively inexpensive. So for I've seen it starting at, let's say, $60,000 for this launch, and then we get a little bit more expensive if you want to go in sun-synchronous orbit. I will talk a little bit about that later. You start at let's say $100,000. But here you get more interesting maybe illumination properties if you want to do Earth observation, or if you want to optimize your thermal or power budget. And then we have not so common geotransfer orbits, which are the orbits that rockets inject into if they want to put a satellite on the geostationary orbit, which is pretty eccentric, gets you pretty far out if you need that. But yeah, it's much less common than the previous two. So what is the drivers on your orbit selection, if you can select? So the distance to the Earth's surface, for example, is important if you consider the power you need to transmit your data or get commands back to the satellite. The illumination is important because different orbital planes have different vectors to the sun, so you have different times in the shadow of the Earth, different times in sunlight. This not only messes with your power collection, but also with your thermal behavior. And here you also have variations over the year, because the Earth moves around the sun. That's known. Yeah? So then the next thing is radiation. So if you don't want to study the Van Allen belts, keep out of the Van Allen belts. These are in the medium Earth orbit range. And if you stay there for long, then you probably get just resets all the time. And something which might not be as obvious is there is an implicit lifetime limit. So this is not yet legislation, but in general, it will be probably pretty soon that every CubeSat put into space must be re-entered before 20 years of its lifetime, just to reduce the amount of space debris. Not every CubeSat launched last year has kept this limit, so we'll probably have a much longer lifetime in orbit. But many CubeSat launch providers now require to show that the orbit you launch in is compliant with this. This also is, of course, dependent on the type of CubeSat you have, and there are currently things in development which reduces your lifetime. So, for example, balloons which inflate or things like that. So about the sun-synchronous orbit, because I found this interesting. So if you would just have a normal undisturbed orbit, and you would move along an orbital plane, then as the year progresses, the plane wouldn't change because it's static in the inertial frame. So you see the illumination conditions here. You have a midnight-noon orbit, named after the time zones that it's flying over, and then it changes to a dusk-dawn orbit here, because it moves along the so-called terminator line between light and shadow here. If you have a sun-synchronous orbit, you're using the fact that the Earth is not a perfect sphere. It's slightly oblated, so this distribution of mass here exerts a force and tends to rotate your orbital plane. And if you're going into just the right inclination, so just the right angle between the equator and your orbital plane, then this will rotate it such that as the Earth moves around the sun, the orbital plane rotates with it. So here you can see that approximately at each time of the year, the orbit is stable. And then you just need to choose which basically local time you have here on your satellite. So here, for example, you would always have a midnight-noon orbit, but you could also always choose a dusk-dawn orbit. So this would dusk-dawn orbit would mean that nearly always you are completely with one side in sunlight. This is good for power, maybe not so good for thermal, but that's a trade-off you have to do. So something about CubeSat transports. Of course, you don't only want to build your CubeSat, you want to maybe keep it stored at your university or hackerspace location, but then at some point you have to transport it to your CubeSat launch provider. And there, of course, it's obvious you want to prevent excess humidity, particle contamination in electrical static discharge and mechanical shock, but you also really have to think through your whole transport chain. So, for example, if you want to transport your satellite in your hand luggage at the airport you might be asked to open it. And this is especially bad if you have taken extensive measures to keep humidity and particles away from the satellite. So I also heard stories about experiments headed to Mars which were asked to be opened at the airport. So please make sure in advance that you don't get into any problems like that. And of course, then also after the transport, you want to check for transport damage. And if you can't look into your satellite anymore, maybe think about that. How do you can verify that there really was no damage? Just have a basic check. So yeah, I hope I could give you a small glimpse into the development and what kind of peculiarities there is in satellite and CubeSat design. If you're interested in things like that, I think it would be best if you look up other CubeSat projects reports. Usually they especially if they're university projects, they write papers about operation and so on. And there are lots of interesting things to find here. And I just want to remind you that verification is key. So if you have a thing that must work, then you have to test it. Otherwise, you can just think it probably won't work. And if there is something, a risk you take, then think about a plan B. So if the fault occurs, what do you do? Is there any mitigation? At least you can do maybe a reduced set of science measurements or things like that. So yeah, and this is the end of my talk. I hope it was interesting for you. And I think we can do Q&A now.
Yes. So thank you very much. So for now, as usual, please line up behind the microphones while we see if we have questions from the internet. I don't see our signal angel standing, so just line up. It was a really interesting talk, by the way. So, oh yeah, please leave the room quietly because we are still wanting to hear the questions that might occur. And as we can see, there are many, many questions. That's interesting. Okay, we'll just start over there.
Hi. Hello. Does it work? Hello. Thanks for your talk. I've heard about Intel Edison boards, hacker PCB, something like that, used for CAN-SAT. Do you know about any hacker PCBs like Raspberry Pi or Arduino clones which are which can work at the space fine?
Well, depending on how you build it, it's more the question of how well it will work. So as I showed you about radiation, there are some things you have to design around for and so on. So there was, at least with Arduino, I know for certain that there was a mission which used Arduino at least compatible hardware as onboard computer, but this was also, if I remember correctly, mostly done so that other people can program for the satellite. So it was more used as a compatibility thing and not for any other obvious advantage in hardware architecture or programming.
But these PCBs are not specified for such circumstances, such conditions.
Well, the problems you might get with just commercial off-the-shelf PCBs for Raspberry Pi or so are, for example, as I showed you, these soldering whiskers, because they are certainly produced without lead in their solder. And there have been even full commercial satellites which failed due to soldering whiskers. At least that's what they think it was. So this might be a problem. And then, of course, yeah, just the whole way it structures might not be ideal to mount inside a satellite, but that has to really depend on the PCB. I can't give you a general answer for that.
Thank you.
Okay, then we have two questions from the Signal Angel. So,
Yes, on IRC they're asking, Photon is asking if there are any satellites up there that can be used freely and legally by hobbyists.
Well, if you're a licensed amateur radio user, then there are some amateur radio satellites up there. So then you get, most of them are relay satellites. So you send analog signal, usually sound, up there, and then it just gets repeated on a different frequency down. But there are also, I'm not sure if there's anyone active right now, but there is also some amateur radio satellites in the past which used some kind of message boxing technique to transmit messages. But as I said at the beginning, you have to need an amateur radio license to use these satellites.
And the other question is from Handsome Pirate, asking if you would recommend to use a red-hardened CPU and memory.
Well, the problem with these are, if it's really red hard, then they cost usually a lot of money because they have small lots and so on. And there are usually, at least that I know of, not many CubeSats which use this kind of technology. So at least the consensus among the CubeSat design seems to be that you should rather design around the radiation problem than to just select hardened components. Because especially if you are using the CubeSat form factor because it's cheap, maybe you can accommodate for a certain failure rate, then you don't want to get into this expenses with red hat components.
Okay, then we have questions here on the For You left side.
Yes. I have one comment and one question actually. And the comment is, if you think about orbit, think latency, especially if you do communication. Because at certain altitudes, the speed of light actually is your limit for communications, and it takes a while to get there. And if you especially go in high orbits, like geostationary orbits, you have significant delays. So that's from my experience with geostationary satellites. But my question is also regarding orbits. Till what orbit do you know is GPS available, or is it available at all?
Well, there are lots of tricks. I mean, GPS are used on CubeSats. The problem is that if you just buy a GPS receiver off the shelf, there are these limits built into it usually, so that you don't use it to build intercontinental ballistic missiles. So they have a speed limit and an altitude limit. And while on high altitude balloons, you usually get away if you find something which needs both of them violated to shut down. On a satellite, you violate both of them. So either you need some special firmware for that, or use a component which is built to meet these requirements. But of course, those get pretty expensive. So it's definitely possible to use GPS, especially on the low Earth orbits, because GPS is more like a medium Earth orbit. But even if you are above the satellite, the GPS satellite orbits, there are, I'm not sure if I think it has been used already, but the antennas of the GPS satellite try to illuminate basically the whole Earth, but they have some overspill. So if you look at the Earth, then a GPS satellite coming from the other side might send you a signal. And by tricks like that, you get also some GPS reception on higher orbits. So it is possible, it has been done, but I don't know of any just component you can grab for that.
Interesting. And one more thing. Are you familiar with the OuterNet project? The OuterNet, which is actually an attempt to build a global internet with CubeSats. But they are not very far yet, I guess. But have you ever heard of that?
I'm not completely sure. I heard of one project which I think wanted to use, I'm not sure if it was CubeSat, I think they used just regular communication satellites to distribute information. But I'm not sure if this is the same project.
I think it is. They're using the existing satellites to just broadcast things like Wikipedia and stuff. But
yeah, as I said, if you just use, let's say, amateur radio frequencies, then your bandwidth is pretty small. The problem is also in low Earth orbit. Of course, the satellite just whooshes by, so you maybe have a 10-minute contact window, and you don't get a lot of data down this time.
yeah.
And So if you will really want to distribute a lot of information, then you might have to think about how to time it and how to maybe use multiple satellites.
Yeah,
And of course, transmission on the satellite is often some of the more power-hungry things. So if you're looking at your overall power budget, this might also limit the time you can transmit at all.
and you need multiple tracking antennas, which is also a problem.
Yeah. I mean, this of course depends on what kind of signal is sent. If it's a very robust signal which can penetrate even noise or something like that, then maybe you get away with a less directive antenna on your ground station. But yeah, it's of course a trade-off, and yeah.
Thanks.
Okay, we don't have an endless amount of time left, so maybe if you have longer questions, it would be nice if you could ask them afterwards. And for now, on this side, there might be another one.
Just wanted to ask if you have a tip or something where we can get some of the already computed data or something cool, a cool project with CubeSat you can recommend.
Well, if you are just interested in, let's say, CubeSat housekeeping data, then I already mentioned the FunCube project once. They upload all the housekeeping data they have on the satellite. So if you just want to know how just the environment is approximately on your satellite in orbit, then you might take a look at their website. There is a slight problem with the data when you scrape it, is that if they don't have data for a certain time period, they still give you data, but it's just repeated over and over again with a new timestamp. So if you want to scrape the data, you might have to filter it out afterwards. But at least that's where I got some just data on housekeeping.
Okay, again, over here, the usual.
So you told that battery discharge is limited to 20% of the capacity. Can there be used another types of batteries which is more designed for such kind of temperature swings, or I don't know, ionistors?
Yeah, I mean, of course, you can look at the whole range of available batteries. The problem is that while CubeSats often are more volume limited than really mass limited. I mean, often in space you hear about mass and how much it costs to put a kilogram into orbit or something, but in CubeSats it's usually more the problem of putting everything into your small space. So you basically have a similar problem as you have in your smartphone, and that's why they both converge maybe to the same type of technology, because it's so far above the energy densities of other alternative methods.
Thank you.
Before you can ask the next question, everyone that's leaving now, it would be great if you could leave through the door near the stage, because there's already a queue outside, and then it's not getting up wrangled and, you know, many people and stuff. This microphone.
Okay, yeah, thanks for this amazing talk. My question is, how do you maneuver your satellite in a specific orbit once launched? And another question, how does the electronics react under high vacuum condition, such as a capacitor, wouldn't it evaporate?
Yeah, well, of course, you sometimes see, let's say in ground-based vacuum applications, that they just coat their electrolytic capacitors, so it's somehow encapsulated. But of course, if you have a space application, you might try to get just away from these kind of capacitors. The other thing about in-orbit maneuvers, the problem with that is that there you get into, let's say, rocket propulsion territory, and that means you need mass and energy to make any kind of maneuver. And as I said, usually if you would just need a small engine, let's say, a chemical engine might be the way to go. But you are not allowed to have dangerous substances or high energy content in your satellite, so these kinds of engines usually can't be used. There are some projects at the moment which try to develop, let's say, ion engines, which use the power collected by the satellite to propel medium and thereby generate some thrust. But even if you would think, if they are brought to applications and used, the amount of thrust they give you is not that, the amount of total change in velocity, so-called delta V, is not that much. So you might be able to extend, let's say, your lifetime if you're in a low Earth orbit, but it's difficult to let's say, raise the orbit significantly, or even change the orbital plane. That's very, let's say, expensive. So yeah, it's currently not that feasible in a CubeSat to make big changes. I mean, there are these light sail projects going on. Let's see what they get at, but at the moment, there's no component you can use for that.
Right. So you basically stick with the big satellite.
Yeah.
That is right.
Usually you stay on the same orbit the upper stage left you on. And of course, then you have all this disturbance influences which changes your orbit. But in general, you stay on the same orbit.
Thank you.
Okay, we are out of time. Thank you very much again.